Welcome. The purpose of this training video is to illustrate the destructive forces associated with shock loading. In this case, these destructive forces will be produced by the arresting of a free-falling object. In addition, we will also demonstrate how several items of fault protection equipment are designed to reduce these destructive forces. Come on, let's go break some stuff. What we're using today is a fault protection tripod that would normally be used over a manhole or some other confined space. The tripod would provide an anchorage for the worker's fault protection when he goes down in through the manhole. Today, we're using the tripod as an anchor for the Motion Labs 10,000 pound load cell, and that will record the shock load forces. To create the shock load, we're going to drop a 220 pound steel weight. The reason we use a 220 pound block of steel to simulate a 300 pound person is that when this 220 pound steel block stops, it stops all at once. Every atom stops at the same time. But when a human body is arrested in a harness, what happens is the torso stops, and then the arms and legs and head and neck keep moving for a period of time, which actually reduces the shock load. So we can use a lesser amount of steel to be equal to a 300 pound person. And then finally, we're going to release this 220 pound block of steel using a triple ring release. This type of device is used by skydivers, and if their main chute fouls, they rip the triple ring release and their main chute goes away, and then they can deploy their emergency chute. For test one, we've raised the block of steel up 12 inches. You can note the slack in the aircraft cable, and then we will release the weight and record the force on the readout. 3, 2, 1. We saw that the arrest force was 4,750 pounds on that 1 foot free fall. Look at the damage to the end of the sling. The thimble is totally deformed, and we obviously would never want to use this sling again. For demonstration 2, we're going to drop the weight 24 inches into a 3/8 inch galvanized aircraft cable sling. 3, 2, 1. You can see when we drop the weight 24 inches, the force increased to 7,500 pounds. And we did get some deformation of the eyes of the 3/8 sling, but not nearly as much as we did with the 1/4 inch. For demonstration number 3, we're going to drop the weight 36 inches into a fault protection personal energy absorber. You'll see that the energy absorber will drastically reduce the forces associated with the shock load. 3, 2, 1. As we saw, the arrest force was down to 925 pounds, even though we had a 36 inch free fall distance. The reason is this white material inside the energy absorber ripped away, decelerating the weight to a stop. That deceleration distance in this case was about 13 inches. Had a 300 pound person free fallen 6 feet, which is the maximum allowed by law, we could have had up to 42 inches of deceleration distance in that case. But even if we ripped away all this white material, you would still be caught by the lanyard, because even after the white material is all ripped away, we still have the lanyard going from the top to the bottom. For demonstration 4, we're going to be dropping the weight into a retractable lifeline. The retractable lifeline will catch the weight and then decelerate it slowly over about 40 inches to a complete stop through clutching mechanism inside the unit. Once the device has experienced this load, the bail on the hook will slide up the shaft, revealing a red area. The purpose of this telltale is to warn workers that the device has already arrested a fall and should be removed from service. So if you see a red mark on a shaft on a retractable lifeline you're using, you need to not use it and make sure that it's removed from service and serviced prior to reinstalling. 3, 2, 1. Demonstration number 5 will be dropping the weight into a retractable lanyard. The retractable lanyard, sometimes called a seatbelt lanyard, will stop the load in about 6 inches. This will drastically reduce the shock load. In addition, the webbing material will have some elasticity, which will additionally reduce the shock load down to a tolerable level. 3, 2, 1. For demonstration number 6, we're going to drop the weight 4 inches into the 1/8 inch furlock here. 3, 2, 1. The wire rope is broken at well below its minimum braking strength of 2,000 pounds. For demonstration number 7, we're going to drop the weight 7 inches into an 1/8 inch galvanized aircraft cable sling made up with copper oval nicopress sleeves. This should give the sling a strength of at least 2,000 pounds. 3, 2, 1. For demonstration number 7, we see that it took 2,125 pounds to completely shatter the 1/8 inch aircraft cable sling. In summary, we saw that a 220-pound weight falling only a small distance can produce thousands of pounds of force. For fall protection, this means that it's imperative that we design energy-absorbing systems into our fall protection systems. With respect to rigging shows, many times we use a secondary suspension to back up our primary suspension points in case of a primary suspension point failure. We saw today that a 220-pound weight falling 6 inches can produce 10 times that amount of force when stopping. What this tells us today is that we must not have any slack in our secondary backup systems. Thank you. This video was co-produced by IA Local 16 Training Trust Fund and Stage Rigging. My name is Rocky Paulson. Hang in there.